This video is to show you how to solve problems with constant pressure and constant volume calorimeters. So I already explained the concept and the formulas on calorimeters in the previous video. This video is just to solve some practice problems. And well, just to refresh really quickly, constant pressure constant volume So we said that the constant pressure calorimeter has an equation of Q is equal to M or MCAT equation, MC delta T. M standing for mass, C representing the specific heat, and delta T is just the change in temperature. And while our constant volume is a little modified because it has a heat of reaction, which is QRXN, is equal to the negative specific heat of the calorimeter or heat capacity times delta T, so change in temperature as well. So those are our two formulas. And now let's do some problems. I'm gonna start with one with a constant volume calorimeter. And I forgot to mention that a constant volume calorimeter is also called a bond calorimeter. So bomb calorimeter. So whenever you read bomb calorimeter, it means to constant volume calorimeter. So this problem says 1.15 grams of sucrose, so C12H22O12, goes through combustion in a bound calorimeter. So that's telling us already it's a constant volume calorimeter. And so if the temperature rose from 23.42 degrees Celsius, so our initial temperature is 23.42 degrees Celsius to 27.64, so our final temperature is 27.64 degrees Celsius. So what is the heat of combustion of sucrose? So it's asking us for heat of the reaction. Given that the reaction is combustion, it's just another way of saying heat of reaction, heat of combustion. And they also tell us that the heat capacity of the calorimeter is so C cal is 4.90 kilojoules degrees Celsius. So we have everything we need, and we know it's a constant volume calorimeter, so let's look at our equation. It's the heat of reaction is equal to the C calorimeter times delta T, so that's what we want. Heat of reaction is equal to the heat capacity, so times the delta T. And in this case, if you look at your units, you can see that you don't have to change them into standard units, so you can leave your temperature in Celsius because it'll cancel out. You'll see. So our heat of reaction, just plug our values, will be equal to negative. Our heat is going to be 4.90. I'm sorry, the heat capacity degrees Celsius times delta T. Delta T, I'm going to write it here, is going to be TF minus TI, so 27.64 minus 23.42 degrees Celsius. So by solving that, we get negative 20.7 kilojoules. And well, that's what they were asking. And you may wonder, well, what do we do with the with our grams right here. And well, use your grams if you want, because sometimes your heat of reaction is asked to be in kilojoules or joules per mole. So let's try and find it in kilojoules per mole. So kilojoules per mole is what we're looking for. So let's go to the page. 1.150 C12H22 O12, and we have minus 20.7 kilojoules. So using our mole diagram, you can convert those 1.150 grams of that here into moles, right? So by obtaining the molar mass, which is I think about 342.3 grams. That's 1 mole because it's a molar mass. So the grams cancel out, and I get about 0.0033 moles. That works. So just say 3.3 times 10 to the minus 3 moles. And if they're asking for it on kilojoules per mole, I mean, just by looking at the units, you know that you have to divide your heat of reaction over the number of moles. So minus 20.7 kilojoules per mole, kilojoules over 3.3 times 10 to the minus 3 moles. And that gives us about 6,000 joules, something like that, kilojoules per mole. And well, that's how you find it if they ask it for kilojoules per mole. You have to divide it over the number of moles you have. Now let's go to a constant pressure calorimeter problem. And I chose one that's a little tricky just to cover everything you'll probably see. So you have a hot piece of lead that's 150 grams. So 150 grams of lead. That is at 100 degrees Celsius. Our temperature initial is 100 degrees Celsius. And that piece of lead is added to 50 grams of water. So 50 grams H2O. That is at 22 degrees Celsius. So I'm going to write here lead. And when you add them, the temperature eventually comes to rest at 28.8 degrees Celsius. So the final will be 28.8 degrees Celsius, and that's for both because they're together. And what the problem is asking is, what is the specific heat of the metal? So our C lead is the question. And one thing you must remember is that the specific heat of water is a constant, so at a given temperature, and that is CH2O is equal to 4.184 joules per gram degree Celsius. Because we said it's specific heat, so it's in grams, not molar heat. Let's separate our data from what the process is. That's a horrible line. Alright. Now, in these problems, in which we have two systems, you'll want to do a step before using our equation. And that step is realizing which of the system, which is gaining heat and which is losing heat. And an easy way to do this is to remember that the heat that will be negative is going to be the warm object, because it will get colder, right, if you put it into something that is not as warm as it is. And what will gain heat is going to be positive is the cooler object, because it's going to get hotter. So in this case, our warm object is our metal, or lead, because it's at 100 degrees Celsius. So it's going to be negative Q lead is equal to positive Q water. I mean, and you just have to look at it. Lead is at 100 degrees Celsius and water is at 22 degrees Celsius. You can tell that the lead will lose its heat, will get colder, and the water will get hotter, just by looking at the final temperature. So now we can use our MCAT equation. So it said that the heat of reaction, or no, the heat is going to be equal to mass, the specific heat, and the delta T. And because we have two systems, we have to do it in each side. So it's going to be a very long process. It's going to be the negative side is going to be the mass of the lead, and I'm just going to write it as L, just because writing lead every time is too long. And the specific heat of L, the delta T of L, right? And that's going to be equal to the mass of water, I'm going to write it with a W, times the specific heat of water times the delta T of water too. And the first thing you'll want to do is not to plug in the values, because that will make it even longer than it is. You want to just solve for what you're looking for. In this case, it's the C of the lead, the specific heat of the lead, so just solve for it. So it's going to be Cl is equal to negative O of this side over the mass of the lead, delta T L. And that is, in this case, our equation. And let me write it on the other side real quick. So there we go. We just moved everything to the other page. So just plugging in the values, you will get the specific heat of the lead. Our mass of water is 50 grams. Let me put this 50 grams. This is a negative right here. And our specific heat is 4.184 joules per degree Celsius. And the change in temperature is going to be our final temperature minus the initial temperature of the water. So the final temperature is going to be the same for the lead and the water. So it's going to be 28.8 degrees Celsius minus the 22 degrees Celsius of the water. That is going to be all over the mass of the lead, 150 grams, times the change in temperature of the lead. So it's going to be, again, the final temperature, 28.8 degrees Celsius. But in this case, the initial temperature of the lead, so 100 degrees Celsius. And that is just going to give us 0.13 joules grams degrees Celsius. And that is because the negative goes with this negative sign goes with the negative sign produced in here. So that's why we have a positive, a specific heat. And it usually always is positive. And that is an example of a constant pressure calorimeter.